The question we have today says, why is gravitational field strength G greater at the poles than at the equator? Now, another name for gravitational field strength is what? Acceleration due to gravity. And in physics, we are told that acceleration due to gravity, G, is seen as force per unit mass. Does it make sense? Now, they're asking you, why is this? Now, this is the structure of the Earth. The Earth looks like this. The Earth is not a perfect sphere, so the Earth looks like this. Here, this is the what? The equator. This is the equator, this line, and this is the center of the Earth. We are saying this line is the what? The equator. This is the center of the Earth. So here is the North Pole, here is the South Pole. Does it make sense? Now, here to here. Now we know that if this is a circle, that from here to here is radius of the what? Earth. The radius of the Earth. And from here to here is also radius of the Earth. And from here to here is also radius of the Earth. And from here to here is also radius of the what? Earth. We can see something, right, from this diagram. So they're asking you, why is this one greater here? Why is G greater here? And why is G lesser here? What is the reason? Why is G greater here? And why is G what? Why is G lesser here? So that's the question. Let's explain. Now, from Newton's law of universal gravitation, we know that Isaac Newton stated that force of attraction between two masses is directly proportional to the product of the masses. Let's say, for instance, Earth and the mass. So this is the mass of the what? Earth. So I'm considering the Earth and another mass. Let's say you that is watching this video. Now, force of attraction is directly proportional to the product of the mass of the Earth and you and your mass as well. And this same force of attraction is inversely proportional to what? The square of the distance of the distance between you and the Earth. Do you understand? So if I relate these two things, I'll have that force of attraction is equals the G. This G is universal gravitational constant times mass of the Earth times your mass all over what? Square of the distance between you and the what? Earth. Is that clear? It should be clear. So using this formula, we see that F is equals GMEM all over R squared, right? Now we say that gravitational force is given by force of attraction all over mass of an object. Now this is the mass, this is your mass, this is also your mass from Newton's law of universal gravitation. Now imagine a situation whereby this mass comes down. Now we'll be having that force over mass is equals universal gravitational constant times the mass of the Earth. Mass of the Earth, this is mass of the Earth, all over the square of the distance between you and the Earth. So this force of attraction, this F over M, we say that gravitational field intensity, which is gravitational field strength, is equals force all over what? Mass. So this would be G, small g, is equals universal gravitational constant times the mass of the Earth all over square of the distance, or that's the radius of the what? Earth. And it should interest you to know that this distance between you and the Earth, if this is the Earth and you are the one here, and you look at you and you are this person here and you are this person here, look at the center of the Earth. So from here to here is actually the radius of the what? Earth, which is the same thing. From here to here, radius of the Earth. From here to here, radius of the Earth. Does it make sense? So this square of the distance between you and the Earth is actually the square of the radius of the what? Earth. That's if you are on the surface of the Earth. Is that clear? Now imagine a situation. This thing, if these two things are constant, mass of the Earth, if we assume that G, the universal gravitational constant, and the mass of the Earth are constant, we'll see that the acceleration due to gravity is what? Inversely proportional to the what? Square of the radius of the Earth. So, and we know that in inverse proportion, that if this one is increasing, this one should actually what? Decrease. But when this one is increasing, this one should actually what? Decrease, right? So if we relate this thing that we've said here back to this, what are we going to have? Now, if you watch from here, the distance from this equator to the North Pole, it is lesser than the distance from this equator to the western part, right? Does it make sense? Now it means that The North Pole has small distance from the center of the Earth. Therefore, it will make G to be greater. From what we said, if the distance between you and the Earth is lesser, therefore the acceleration due to gravity has to be greater there. Now, this means that in the equator, if you watch the distance between the center of the Earth and the eastern and western side, do you understand? That's the equator. That the gravitational force, the distance is very big. Therefore, if the distance is very big, the distance is increasing. Therefore, this one has to be smaller. Then it means that the acceleration due to gravity has to be lesser. Does it make sense? So in countries that are on the equator, you can see Kenya. In Kenya, name them in Kiribati, Sao Tome, many of them. Then this country beside Republic of Congo. We have 13 countries. We have 13 countries that are on the equator. 13 countries that are on this equator. So it means that the acceleration due to gravity is lesser there. All the countries that are on the equator on the Earth, and this is 4 of them. We have many of them. There are 13 in number. The acceleration due to gravity there is so much lesser. Do you understand? So have a nice day. Like, comment, share, and follow Courses Academy. Bye bye.